Algo que está. Ah, sí. Ahí
¿Sí
se
está
muestra.
activa?
Sí.
El tiempo.
And start now. I apologize for us returning late. We had to wait for Professor Bray to stop eating. It took a long time.
Never I follow you.
I follow you. So we're going to talk now about dynamic soil properties that control the way the waves pass through the soil, control how ground motions may be amplified or de-amplified, and we'll introduce these concepts that we'll make use of throughout the rest of the course. So the simplest behavior we can have is linear behavior of any kind of material. And if we have linear behavior, the stresses and strains are proportional to each other. And we can characterize the relationship between shear stress and shear strain by a shear modulus. So we use a simple G for shear modulus, and the shear modulus will be constant under these conditions. And we'll refer to it as G max. It's the greatest shear modulus. It's the only shear modulus. It implies that we have infinite strength, though, if we have a purely, strictly linear material. No matter how large the shear stress gets, the shear strain is proportional to it. We characterize this behavior by a shear wave velocity that is the square root of this maximum shear modulus divided by the density, rho, of the material. And we can calculate G max, the maximum shear modulus, from the shear wave velocity. And so the shear wave velocity is a very important property of the soil because we don't really usually measure the maximum shear modulus directly. We measure the shear wave velocity instead and use that to calculate the maximum shear modulus because we can measure shear modulus out in a field where we don't have any effects of disturbance. So that becomes very useful to us. And there are a number of techniques by which we can do this. We'll go through these. Seismic downhole and uphole methods, seismic cone, seismic crosshole, spectral analysis of surface waves, and suspension loaders. We can also use other field tests to at least estimate shear wave velocity. We can correlate it to standard penetration resistance, cone penetration resistance, and perhaps some others. In the lab, we can use Bender elements to measure maximum shear modulus or resonant columns, but we're typically going to be working with samples that have been obtained and brought to the lab, so they're going to have some effects of disturbance. And we see consistently effects of disturbance when we compare field measurements with laboratory measurements. The resonant column test, though, allows us to make measurements at larger strain levels, and we'll see that that becomes very important. So the seismic downhole test or uphole test involves a source of vibration, an impulsive impact type of vibration, and a receiver that can measure stress waves that may arrive at its location. So our source may be a sledgehammer hitting the ground or a beam connected to the ground. It could be an explosive if we're trying to make measurements down to large depths. In the downhole test, the source is at the surface and the receiver is in the borehole. In an uphole test, the configuration is reversed. It requires a borehole, but we may have put in a borehole for exploratory purposes anyway, for drilling and sampling, and so we can make use of that borehole to perform downhole and uphole tests. We usually measure the arrival time of waves at the receiver, moving the receiver in a downhole test to different depths, and the slope of this arrival time versus depth plot is the shear wave velocity. Here we're showing both arrival of P waves, which travel faster, and S waves, which arrive later. And so we can measure P wave velocities by the slope of this curve, and S or shear wave velocities by the arrival time on that curve. As we go deeper and deeper, we know that high frequencies, which give us a sharp signal at the receiver, start to get gapped out. And so the arrival becomes less distinct when we get to larger and larger depths. And so it makes it more difficult to detect the arrival, and the accuracy of the measurement goes down. We know the depth, we know the arrival time, we can calculate the wave propagation velocity. If we go down more than 30 to 60 meters or so, it becomes difficult to use this test. The seismic cone test involves placing geophones above the friction sleeve in a cone penetrometer. And we may have one or ideally two geophones separated by some interval. As we push the cone down into the ground, we're automatically coupled well acoustically to the ground. The cone is in good contact with the ground. That can be a problem with geophones that are put into boreholes, but it's not a problem here. And we can measure the arrival time at the geophone if we only have a single geophone, but if we have two, we can measure the arrival time, the difference in arrival time between the upper geophone and the lower geophone, and make a measurement, therefore, of the shear wave velocity at a depth between the two geophones, rather than having to work with only a single arrival time, where we tend to get an average of the velocities over a larger distance. So we have our geophones mounted, measure their travel time, and we can get an interval value, which can give us some increased resolution when we have two geophones. Crosshole tests involve two or more boreholes, where we put a source and receiver both in the boreholes at the same depth. And so if we're working in a layered soil profile, it allows us to make more accurate measurements of the velocity of individual layers, at least providing that the layers are continuous in a horizontal direction. Sometimes there's differences in the way the source and the receiver are coupled to the side of the boreholes that can lead to a small difference in the arrival time. And so we may put in another boring and have two receivers that are coupled to the boreholes in the same way, so that any delay that's caused by imperfect coupling is the same in both, and the arrival time difference is not affected by it, or at least it's affected in the same way. So we get velocities of individual layers this way very efficiently. We have to keep track of our boreholes and make sure that we're drilling them straight, or at least we know how far apart they are as we go deeper. As we go into a deep boring, the borehole may wander off and not be perfectly vertical, so we need to be able to account for that, because we need to know the distance between the receivers in order to make an accurate measurement of the velocity. And it can be more costly to do this, but it can be a good option in some cases. Spectral analysis of surface waves, or SASW testing, makes use of measurements of Rayleigh wave performance. Rayleigh waves are surface waves. We'll talk about them in more detail a little bit later, but it's important to recognize that they induce deformations in the soil at shallow depths. Below about one wavelength, their amplitudes are quite small. So if we go down, somehow this has gotten truncated. If we go down one wavelength below that depth, the displacements are much smaller. Now, wavelength is a function of the frequency of the loading. And so if we have a very high frequency, our wavelength is short, and the Rayleigh waves are traveling through shallow soils. For lower frequencies, the wavelengths are longer, and the Rayleigh wave is traveling through deeper soils. And it's the stiffness of the soil that the Rayleigh wave is traveling through that will control how quickly that Rayleigh wave travels. And so if we're in a material that has a uniform stiffness, if the stiffness is constant with depth, then shallow Rayleigh waves and deep Rayleigh waves will travel at the same speed. And so the wave propagation velocity will not vary with the frequency of the wave. So we would say that those waves then are non-dispersive. But in real geologic materials, the stiffness usually increases with depth. You have higher confining pressures at greater depths. We're usually dealing with older materials that tend to be stiffer. And so low-frequency Rayleigh waves that extend down to large depths will travel faster than high-frequency Rayleigh waves that are confined to the shallower, softer materials that travel more slowly near the ground surface. So if we set up an SASW test, we'll put out a couple of sensors. I need to catch up with with what I'm saying. We'll put up a couple of sensors, and we'll apply at the source some vibrations that have many different frequencies in them, maybe due to impact, or we may have some vibration source that can put in white noise or a broad range of frequencies. And so at the receivers, we'll make measurements of the motions that are recorded, and we'll use a Fourier transform to transform them to the frequency domain. So we can take some signal, it may be an irregular, transient, noisy signal, and represent it through a Fourier transform as the sum of a bunch of sine waves with different amplitudes, different frequencies, and different phase angles. And so we'll take the motions recorded at these two receivers, and we know the distance between them. We'll take the phase angles, the shifts in time of the different frequencies, and divide them by 2 pi times the frequency, and we get an apparent travel time for each frequency. So if we know the travel time for each frequency, and we know the distance over which that travel occurs, we can calculate a radial wave velocity for each frequency. And we can convert that to a radial wave velocity for each wavelength, because wavelengths and frequencies are related to each other. And if we plot them, we'll see something that looks like this in a typical site. As we go to longer wavelengths, the lower part of the plot here, we're distorting the soil, exciting the soil to greater depths, and if the soil is stiffer at those greater depths, we'll see higher velocities. And at shallow depths, our short wavelengths will be passing through softer soils. So we then take an analytical solution for the response of surface waves in a layered elastic half space, and we calculate by an optimization process, we determine the combination of layer thicknesses and layer velocities that match these curves. So we call these dispersion curves, and by going through this optimization analysis, we can represent the behavior of the soil at the site by a series of layers of constant shear wave velocity. And so by minimizing the error between the computed and the measured velocities, we can come up with a dispersion curve and a shear wave velocity profile. In order to get down to large depths, you need to have a source that can have a lot of power at low frequencies, which means you need something that's very heavy. It's not very common equipment, but there is some, particularly at the University of Texas. Professor Ken Stokey, who was instrumental in developing the SASW technique, has some equipment, one he calls T-Rex, like the dinosaur, one is called the Liquidator, and they can provide very heavy loads oscillating very quickly in order to get down to large depths. I've worked with him on a project at a nuclear waste site in eastern Washington in the U.S., and we went down to about close to 400 meters with the SASW testing using this large equipment. The suspension logger is a newer test, and it consists of a long probe that's lowered down into a borehole that's filled with fluid. And there is a vibration source that's typically a solenoid, a mechanical device that produces an impact that causes waves to travel out into the fluid within the borehole, and the waves are detected at this lower geophone and then the upper geophone. So some of the wave energy travels through the fluid, but some of it goes out into the soil, travels upward, and interacts with the wall of the borehole to send waves back into the fluid. And so the developers of this device developed signal processing software that can remove the fluid, the wave that goes through the fluid, so that you are left with the wave that goes through the soil. And so by measuring the difference in arrival times of that wave in the lower and upper geophone, and knowing the distance between them, you can measure the velocity of the wave that has traveled through the soil. So we can measure P wave velocities and shear wave velocities this way. The results correlate well to downhole and crosshole tests. And the source travels down the borehole with the receivers, and so the distance between the source and the receivers doesn't change, so you can go to very large depths without losing quality in your signal. And so it's been used down to depths of 1 to 2 kilometers. The waves that are produced are very, very high frequency, and in some soils, the wave propagation velocity is frequency dependent or rate dependent. And so you may need to make a correction to go from these very high frequencies of, say, 500 to 2,000 hertz down to 20 hertz or so, which is about the highest frequencies that we're interested in for earthquake engineering purposes. They tend not to be reliable at very shallow depths, but we have other tools we can use there. In a lab, we can use a resonant column test where we have a cylindrical sample of soil that has a top cap, just as we would in a triaxial test, but that top cap has arms that extend out from it with magnets attached to those arms. The magnets are contained in electrical coils, and when a voltage is applied to the coil, the magnet tends to move. It wants to move in a horizontal direction. And so these are wired so that applying, say, a positive voltage will apply a torque to the top of the sample. And if we apply a negative voltage, it will apply a torque in the other direction. And so without really touching the sample mechanically, we can apply torque to it. And so that's what we do in this test. We have these magnets that are attached to our top coils, going through coils, and we can apply torque. If we apply a harmonic voltage, a sinusoidal voltage, we can achieve a harmonic torque. So in this test, we'll apply initially a low amplitude voltage to produce a low amplitude torque. And that will induce very small strains in the soil. And we'll start with a low frequency. We'll measure the amount of rotation that this torque causes. Then we'll increase the frequency and sweep across a range of frequencies. And what we'll see is that there will be some differences in the amplitude of the motion, even though the torque is constant, as a function of the frequency. And at the natural frequency of this system, which is going to depend on the mass and the polar moment of inertia of this assemblage of magnets and the arms they're attached to, and on the characteristics of the soil sample, we can calculate the shear modulus from that measured natural frequency. And so that gives us an estimate of G max. The width of this figure, if we was to draw a curve through this, the width would be an indication of the damping characteristics of the soil. So we make use of that as well. Bender elements are piezoelectric materials that are bonded to each other. A piezoelectric material is one that, when a voltage is applied to it, it will expand in one polarity. If the opposite polarity is applied, it will contract and get smaller. So we bond these things to each other. They're essentially glued to each other, such that one will expand and the other will contract. And so when a positive voltage is applied, the large one pushes the one that expands, pushes the one that contracts in the other direction, and then when it's reversed, it goes back the other way. And so if we apply a sharp voltage pulse, we get a sharp, we do sound effects too, we get a sharp impact, and a wave travels through our sample. So if we push these things into the top and bottom of a sample, and we apply a voltage pulse, it will travel through the sample and reach the other bender element. So if you take a bender element and you move it mechanically, it will produce a voltage. And so we can apply a voltage, say at the bottom, measure the voltage at the top, see what the time difference is, the travel time from the bottom to the top. We know the separation distance, so we can calculate a shear wave velocity that way. Then our sample hasn't been disturbed by this, so we can go ahead and perform a triaxial test or whatever type of test we want to use. We can put these into simple shear or consolidation samples and make these measurements essentially non-destructively. This low strain stiffness, and all of these tests are inducing low strains in the soil. We have seen experimentally that it increases as the effective stress in the soil increases. As the void ratio decreases, and denser soils will be stiffer than looser soils. It increases with geologic age, with the presence of cementation. Over-consolidated soils tend to be stiffer than normally consolidated soils. There's not a large impact of plasticity, and we can see changes in the number of loading cycles when we have lots of loading cycles applying. And it can be different for clays and sands. There is also some uncertainty in this value, and we're increasingly want to account for uncertainty in our analyses at a given site. So soil conditions are going to vary from one location to another. The uncertainty will be affected by how many measurements we're able to make and how those measurements are made. If we go to the site and make measurements of the shear wave velocity at the site, we generally have a standard deviation of the natural logarithm of the shear wave velocity of about 0.15 or so in the upper 50 meters, and it'll go up to about 0.2 for greater depths. If we just use site classes or crude correlations, our uncertainty will be much higher. And so we should recognize that there's a real benefit to making site-specific shear wave velocity measurements. It's one of the most fundamental characteristics of the soil. It's one of the things that influences site response the most, and it's a good exploratory tool as well to help us identify soils and changes in the soil. So there's really, with the advent of things like a seismic cone, there's very little reason, acceptable reason, not to be making shear wave velocity measurements if you're dealing with dynamics problems. So we have linear elastic behavior, and at these very low strains, the soil will behave generally in a linear elastic way. But soils are not linear, they're nonlinear. We could have a nonlinear elastic material. If we did, we would see some stiffness that would be higher at low strains, but as we went to higher and higher strains, the stiffness would reduce. It would be the same in both directions. If the soil unloaded along the same path that it loaded on, we would say that the material is nonlinear elastic. But not very many materials behave that way. Soils in reality are nonlinear and inelastic. And so while we may, under low levels of loading, see loads that increase and just show a little bit of nonlinearity, when we unload, we're going to follow a different path down. And if we reload, we're going to go back up and be left with a hysteresis loop. And the area inside that hysteresis loop is a measure of the work that's done or the energy that's dissipated by the soil in that cycle of loading. If we use a higher load, we're going to see greater strains. We'll see a lower overall stiffness. If we drew a secant line through the tips of these hysteresis loops, we'd see that the green one would be flatter than the blue one because the strain amplitude is increased. If we went to a higher stress level and strain level yet, we would see a wider hysteresis loop indicating that more energy is being dissipated, that our damping is higher, and we'd also see that the stiffness was lower. So this is how the soil, is going to behave. At a given strain level, we'll have a certain stiffness. So we could call that G at the strain level gamma 1. If we are to use a viscoelastic model to represent our soil, the viscoelastic model has an implication that the stress strain curve is an ellipse. And for low levels of strain, it's a pretty good approximation. It works quite well. As we go to larger and larger levels of strain, that accuracy of that approximation will decrease, but we can find an ellipse that has the same area as the hysteretic stress strain loop and calculate an equivalent damping ratio. So our stiffness and our damping ratio will correspond to this strain level gamma 1. If we go to a higher strain level, we'll have a softer stiffness, so G at gamma 2 is going to be less than G at gamma 1 was. We'll have to have a fatter hysteresis loop, but it may still make a pretty good overall approximation of the average stiffness and the total amount of damping that's achieved. When we get out to very large strains, however, we can see that the stiffness of the soil is changing quite a bit. the average stiffness of our loop, of our ellipse of constant area or equal area doesn't look very much like our stress strain curve anymore. And so the approximation becomes weaker. In an average sense, we're capturing the softness, the softening of the soil, and the increase in energy dissipation, but at different points around each of those hysteresis loops, the behavior is quite different. So there's a couple approaches we can take to deal with nonlinear behavior of the soil. One is to use a nonlinear elastoplastic model where we actually explicitly model the nonlinear inelastic behavior. The other is to use what we call an equivalent linear approach, where we're going to use a viscoelastic model to approximate the nonlinearity. And we'll see that the viscoelastic equivalent linear approximation is good up to a point, but beyond that point, we need to turn to nonlinear models. So to capture the nonlinear behavior, we can go back to the resonant column test, where we may have started with some low level of torque, a low level of strain, which gives us a high shear modulus, and then start increasing the level of torque. If we increase the level of torque, the angle of rotation is going to change, and because the soil is nonlinear, it's going to behave more softly, and its natural frequency will be lowered. And if we continue this process, we can measure the natural frequency at different strain levels, and by looking at the width of those curves, we can measure the damping ratio at different strain levels. And we'll see our resonant frequency dropping, our bandwidth, the width of those bands increasing. We'll get our shear moduli and our damping ratios, and when we plot them, we'll see that at very low strain levels, we have a logarithmic scale shown here for the strain. The stiffness is equal to this maximum stiffness, but then it decreases as the strain level increases. Our damping ratio will have a low value at small strains, but then it's going to increase as we go to larger strain levels. We usually normalize the curve on the left by dividing by Gmax so that we have a modulus reduction curve. And that shows us how the stiffness is decreasing as the strain amplitude increases. And for different soils with different degrees of nonlinearity, these curves will be different. The more nonlinear the material is, the faster those modulus will be reduced, and the greater the damping will be. So we have different curves for different material behaviors, and they behave in this way. So in the equivalent linear approach, we'll see three ranges of behavior. The first one exists below a threshold, an elastic threshold shear strain. And in that range, this ratio of G over G max is approximately equal to 1, indicating that the stiffness is essentially constant. And once we go beyond this range, though, the soil starts to behave nonlinearly. The stiffness will reduce. There's another threshold strain that's very important, particularly when we're looking at liquefaction problems and the generation of pore pressures in soils that are loaded cyclically. And that's the volumetric threshold strain. This strain, if we were testing, say, a dry soil, like a dry sand, below this strain level, we would see some nonlinear behavior, but it would be elastic. The particles would not be slipping and sliding with respect to each other, and there would be no volume change, no tendency for those particles to move into a different configuration, even if it was loose. But when we go beyond that strain level, the volumetric threshold strain, then in that dry sand, the particles start to slip and slide with respect to each other, and we'll start to see some volume change. Under undrained conditions, when we go beyond that volumetric threshold strain, that's when we start seeing pore pressures building up. Below that, we may have some cyclic changes in pore pressure, but at the end of our loading, the pore pressure would be what it originally was. But under undrained conditions, when we exceed that volumetric threshold curve, that's when we start seeing pore pressures increasing. And Professor Gray will talk in more detail about that a little bit later. So we have this predictable behavior, and people have made predictions. Art and Drenovich, in the very early stages of soil dynamics, used a hyperbola. A rectangular hyperbola is characterized by a maximum shear modulus and some strength in order to describe the shape of a backbone curve. So this is a stress-strain relationship. If we take the shear stress as G times gamma and then divide by G max, we can show that this modulus reduction curve that corresponds to this would be of this form. It would just depend on this reference strain that is the strain at when the shear stress is half of the shear strength. And there's a corresponding relationship that can be developed for the damping ratio, but we get in their relationship a simple curve that looks like this. The damping ratio was taken as 1 minus the modulus reduction ratio. That has advanced over the years. Those were recommended as being appropriate for all soils. In the early 1990s, Idris suggested that there should be a different curve for sands than for clays, that sands were more nonlinear than clays. And so a sand's stiffness would start to decrease at a lower strain level than a clays would. But the idea then was that you couldn't distinguish between the damping characteristics of sands and clays. Now we have a lot more data, and people have looked at it more carefully, and we have improved models for modulus reduction and damping curves. And those of Darandelli, working with Professor Stokey in Texas, are the most commonly used. It uses a relationship for the shear modulus reduction that depends on two parameters, a reference strain and an exponent here. And those allow more flexibility in the shape of the modulus reduction curves. So this reference strain allows us to shift the curve to the left and right, and the exponent A allows us to make it steeper or flatter. And so these characteristics have been used to defined for different soils. The damping ratio is affected by similar characteristics, and it has a B term that influences its value. And so there are 4 parameters that are required here: the reference strain, gamma R, the exponent A, the coefficient B, and a minimum damping ratio. And Darandelli provides relationships to allow us to predict that as a function of parameters that we can measure pretty easily, like the plasticity index, over-consolidation ratio, effective stress level, and so on. And so this is quite commonly used in practice. Darandelli's models show that non-plastic soils are more nonlinear than highly plastic soils. This is something we learned in the 1985 Mexico City earthquake. There's behavior at high and low effective stresses. For low plasticity soils, we see similar types of behaviors affected also by the confining pressure. Deeper soils with higher confining pressures behave more linearly than shallow soils at lower confining pressure, both for low and high plasticity indices. The effective plasticity can be seen on damping ratio as well in these plots. These are what the equations predict. We should be careful not to rely on these at shear strain levels greater than about 0.5 to 1%. The resonant column test is good up to about that level. These magnets and the arms that they're attached to will start to hit the coils at shear strains of about that level, and so we can't make use of the data beyond that point, even though the equations in Darandelli's dissertation allow you to go out to larger strains. So this crossing that we see here and the reduction is really not in a range of that we can rely upon data-wise. It's just a function of the mathematical functions they chose to use. There are some exceptions. Some soils are structured. They may be cemented. They may have sensitive soils. Granite clay is one of these. I'm going to pass through this pretty quickly. Professor Bray can talk about this. The student, Javier Bergenauer, worked on this. I see if I opened up an old file, so I'm taking that out. Darandelli also allows characterization of uncertainty in the modulus reduction relationship. and in the damping ratio. And so we have tools for estimating uncertainty in Gmax, now in G over Gmax, and in the damping ratio. And in some site response analyses, when we want to characterize uncertainty, we'll randomize these properties and perform many analyses that allow us to come up with distributions of ground response rather than just single values. The linearity or nonlinearity is what's controlling these aspects of behavior. When we have high degrees of linearity, we have low damping. And when we have low degrees of nonlinearity, we have high damping. And so they're negatively correlated with each other, and we usually assume a correlation coefficient of negative 0.5. For non-plastic soils, Mung followed Darandelli at Texas, and he came up with modulus reduction and damping relationships that are influenced by the grain size distribution. So the coefficient of uniformity of the soil becomes important for non-plastic soils, say for sands and gravels. And so uniformly graded soils tend to behave more linearly than well-graded soils do. So these types of relationships are also available. You have these in your notes. Other types of materials, gravels, Rollins developed material damping and modulus reduction curves for gravelly soils. They tend to be more nonlinear than sands. There are modulus reduction and damping curves available for municipal solid waste materials. Demetrius Zekos, working with Professor Gray, developed these. We can look at very large strains. We have to be concerned in soft soils or soils subjected to very high levels of shaking. We have to be concerned with the shear strength of the soil. When we take these modulus reduction curves and the equations that represent them, we have to recognize those correspond to low strains, less than 0.5 to 1%. We're mobilizing shear strength at much, much larger strains. And if we simply rely on the form of the equation, whether it's a hyperbola or a modified hyperbola, to extrapolate from those low strains all the way out to strains that are 10 or 20 or 50 times larger, they may not be accurate. In most cases, they're not going to be accurate. And so we need to account for the strength of the soil as well. And that may require that we modify our modulus reduction and damping curves to account for the actual strength of the soil. And we do that typically by a procedure where we'll identify a strain range that we think our modulus reduction and damping ratio applies to, and we can use that modulus reduction relationship, Mgmax, to calculate the shear stress and the backbone curve, the stress strain curve at that level. We can then use a simple hyperbola that has this stiffness at that strain level and a correct strength to extrapolate out from the low strain behavior to the correct high strain behavior. And so site response codes are available now that will do that for you, but you have to pay attention and make sure that it gets done. This way we can get a continuous smooth behavior at the intersection. How much effect does it have? Well, here are modulus reduction and damping curves for a granular material. You can see that the strength goes up to about 800 pounds per square foot. This is a backbone curve, a stress strain curve that corresponds to this modulus reduction curve. We're using a log scale for the shear strain, so it doesn't look like a normal backbone curve. If we use a linear scale, then this looks more like a stress strain curve, but these don't look like the way we normally look at modulus reduction curves. But they're equivalent, and we can go back and forth between them. We're looking at the same data, just plotted two different ways. If we had a strength that was 500 pounds per square foot instead of 800 pounds per square foot, we can apply the type of correction that I just showed. And it's shown here that our strength is coming up and it's smooth and asymptotic to 500 pounds per square foot. This is the uncorrected value. This is the corrected value. If we look at the modulus reduction curve, the blue line is the corrected value, and the gray line, which you can barely see, is the uncorrected value. So very small changes in the modulus reduction curve at large strains can lead to very large changes in the larger strain stiffness behavior. If our strength was 300 PSF, we could do the same thing. We would see then a more significant difference here, but we're reducing from 800 to 300. It's not a huge difference in the modulus reduction curve. So these are things that we need to pay attention to. There are nonlinear models, one-dimensional non-cyclic nonlinear models that are characterized by a backbone curve, a stress strain curve, and some unloading, reloading rules. And there are also advanced constitutive models, plasticity models that have elastic regions, yield surfaces, flow rules, hardening laws, and all of those types of features that allow them to be more general. If we look at cyclic nonlinear models, we often use the Bayesian criteria, which can be effective. They consist of a series of rules. The first rule is that we follow the backbone curve for the first quarter cycle of loading. Then we expand that initial backbone curve by a factor of 2 in both directions, and we use it to follow the rest of the curve. One word of warning with Bayesian criteria is that they tend to over-predict damping out of large strains. Because the unloading reloading curves have the same shape as the original backbone curve, there's no real flexibility on how the damping ratio behaves. And so they can tend to over-damp the behavior at large strains, and that can have an effect on site response when we're using it in that kind of application. But there are codes now that will correct for that as well. So when we're dealing with continuous media like soil and rock, we best handle these with wave propagation theory. And the propagation of waves through materials depends on the stiffness, density, and damping characteristics of those materials. Stiffness is most important, damping is next, and the density is a little less important, largely because it doesn't vary that much for different soils. We know that wave amplitudes will increase when we go from stiffer to softer materials. We know that they will decrease as we move further along some travel path due to material damping and geometric spreading. We know that the stiffness of the soil will decrease as our strain amplitudes increase. And our greatest stiffness will exist at very low strains. That's our maximum shear modulus that we'll usually measure out in the field by measuring shear wave velocity and computing Gmax from it. The rate at which stiffness decays depends on the plasticity of the soil, depends on the effective stress, can also be influenced by over-consolidation ratio. Damping is characterized by influenced by the same parameters. And so as our stiffness degrades, the rate of damping increases. We can use equivalent linear properties to characterize the main effects of nonlinearity, but we can do it more accurately with nonlinear models. So I'll conclude this part there. We'll be talking about these principles more throughout the rest of the course, and they have important implications. So it's not the last that we will see of these. I think their importance will become even more clear to you as we proceed. Okay, thank you.
If you have questions while we change over, please ask them.
Questions? Yes.
Ya la tuviste.
With regards to the shear modulus degradation curve, effect of different tests, cyclic traditional test versus rotational shear test, what's the effect? Does it shift the curve or? For the shear modulus degradation curve, if you measure the modulus in different type of tests, at large strains.
Yes.
Sometimes you can do a cyclic trajectory test, right? And sometimes you do a rotational shear test, and what's the effect on the curves?
Well, we can measure it in a resin column test. We're applying torsional shear to the sample, and so the strains that we're measuring are strains on horizontal planes, and we normally, as we start talking about site response, we make the assumption typically that waves are propagating vertically with horizontal particle motion. So we call these vertically propagating SH waves. And in torsional shear, we are shearing the soil in the same manner. Now, there can be some inaccuracies in a solid resonant column apparatus because the strain varies from the center of the sample out to the perimeter of the sample. So we usually compute an average strain there that we're characterizing. We can improve that by using hollow cylinder tests where we have a much more uniform strain. In a simple shear test, if we were to measure stress strain behavior in a simple shear test, we would also be shearing the soil on horizontal planes. In a triaxial test, we're shearing the soil on an inclined plane. And so the fabric of the soil may come into play more there. It certainly can come into play in other tests as well. But if we typically have some sort of horizontal bedding, then we're going to be less accurate in a triaxial test. In triaxial and simple shear types of tests, we have problems for measuring low strain dynamic properties because of compression of the planes at the top and the bottom of the sample. Some people perform cyclotriaxial tests with internal strain measurements that will be attached to the 1/3 points of a triaxial specimen to try to avoid the non-uniform characteristics that can exist near the top and bottom of the sample. So the resonant column test is generally the preferred standard for laboratory measurement of the behavior at larger strains, and a big part of that is the fact that it's shearing the soil in the same way that waves are going to shear when they come up from below. Okay.